So good afternoon, everybody. My name is Narasimhen. I'm an engineer at Hesperus, one of the organ-on-chip companies located in Orlando, Florida, in the USA. Today, I'll be talking about a high-throughput platform to study cardiac ischemia, which consists of microelectrode arrays and silicon cantilevers, piezoelectric cantilevers, and piezoresistive cantilevers to look at different in situ monitoring techniques that we can use. Uh, as everybody is familiar in the room, when you're looking at human cell-based assays, some of the important things to consider are going to be your microfluidic device design itself, in which case a lot of modeling is done to find the optimal flow rates, etc. The microenvironment, which is looking at the surface chemistry, media formulations, extracellular matrices, etc. And finally, what type of cell types you need for the model that you're using. At Hesperus itself, what we usually want to do is focus on multi-organ systems. That way we can look at organ-organ interaction. What we usually look at when it comes to the microenvironment is the surface chemistry, because we use a lot of different BioMEMS chips that require matching of the ECM and also to be able to pattern them. Finally, we also have to focus on the media formulations, because we're looking at using a single media across different organ types, and it has to be serum-free. So in such a situation, media optimization is critical. And finally, one of the things that we focus on is functional measurements. What are functional measurements, right? Functional measurements are essentially mechanical or electrical readouts that you can get from the system, not just biomarker-based. And usually you would want these to be non-invasive, you'd want them to be in real time, and you also don't want them to affect the cells themselves in any way. What are one of the advantages of using these functional measurements? One of them is going to be you can detect minor changes that you might miss if you're really looking at live or dead or biomarker or endpoint assays. One such example would be when you're studying Alzheimer's disease models, you would get mild cognitive impairment before you get a full-blown disease. Such things can be studied when you're looking at integrating functional readouts. So here is an example of one of the most common systems that we use. It is a 4-organ system. It consists of a liver component, a heart component, a skeletal muscle component, and a neuronal brain component. So each of these have functional readouts associated with them. Like I said before, we can divide them into mechanical and electrical. So when it comes to the heart, you can look at something called silicon cantilevers. Think of these as paddle boards. What's happening is you're culturing cardiac cells on these paddle boards, and then you're shining a laser at the very tip, so very similar to what you do in AFM. And then you look at the deflected signal onto a photo detector, and then any deflection of this cantilever is going to produce changes in signal. Now, say you have conditions such as hypertrophic cardiomyopathy, your cardiac cells are going to beat a lot stronger, which is going to lead to an increase in this force, which you can detect. Similarly, for the skeletal muscle, say you have a disease like sarcopenia, where your muscle is wasting away, you'll see a decrease in the force that could be measured similarly. And then finally, when it comes to the electrical component, we use microelectrode arrays. And what we get by doing that is we can culture heart cells on them to look at signals that are very similar to what you might see in the clinic when it comes to looking at an ECG or an EEG when it comes to the neurons. Now, these are very, very useful, especially for the neurons while studying disease models like Alzheimer's, etc., and also definitely for the cardiac. So now moving on to laser patterning, which is one of the things we do. And why do we need to do this? It's because I mentioned microelectrode arrays and silicon cantilevers. The microelectrode arrays are usually very, very small, right? They're, the ones we use at least are at the order of 80 microns. To be able to get the cells to align, as shown in this panel here, because you want the cells to align, we need to do chemical patterning. And this is usually done by using a photomask and a laser. So the ECM for the cells is only on the electrode area that you want it to be. So moving on to some characterization of the heart cells that were used in this model itself. Human-derived induced pluripotent cardiomyocytes were used in this case. What you see in panel A here is just a face image of the cardiomyocytes. Or B, C, and D, what you're looking at is once these cardiomyocytes are patterned on the electrodes, as you see here, what you end up getting is actually the cells align along the electrodes. You get directionality, you get alignment, as opposed to when it's when there's no pattern, you see no actual geometric structure to the cells themselves. Now, this is very important when studying the electrical function of the cells themselves. And then finally, on the right here, you're looking at the myosin heavy chain and just the nuclei. The myosin heavy chain staining just shows that you're getting sarcomere aggregation. Now moving on to the development of the cardiac ischemia platform itself. Why is this relevant? Why is this important? So what is a cardiac ischemic event, right? So when, say, your aorta or any of the arteries leading to your heart essentially clog, your coronary artery, right? You're going to get a heart attack because you're getting very restricted blood flow to the heart. Now, it takes a while with fully restricted blood flow for the muscle to die, but you also have conditions where you have partial restriction. What happens in these cases of partial restriction? You see a lot of electrophysiological changes happening in the heart before you see any permanent damage. Why is that? When the cell reaches a state of hypoxia, in this case, you have reduced ATP, which affects the sodium and potassium ATPase channels in the cardiac cell itself, which leads to depolarization because the hyperpolarizing currents are cut off. What this essentially means is that you don't get the action potential upstroke as fast, which causes a reduction in the conduction velocity in the heart. Other changes also are you see differences in the T wave that you see in the ECG. Usually it's inverted in the case of ischemia, and you also see mechanical deficits to the heart. Now, so we wonder, it would be cool to have some in vitro models to be able to study upcoming therapeutics and things like that in the bench. Right? So along those lines, the first study that was done by our group in this was using a single system which consists of just a cardiac MEA. This is the ICC of the cardiac cells themselves, showing the nuclei and the actin filaments, just showing healthy cells. Here's looking at control activity coming from the microelectrode arrays, looking at beat frequency, which is how many times your heart is beating per second or minute. The conduction velocity, which is looking at the speed of the signal traveling from one electrode to the next electrode, as shown previously. Your conduction velocity will be how fast the signal propagates from here to here. All right, and then the QT interval. So what this shows essentially is that without any stress, the system performs relatively well. And then when the system is exposed to a hypoxic event, in this case, which was essentially 0% oxygen, what we end up seeing is a sharp decline in the conduction velocity after the ischemic event. And then once the oxygen is restored, you see that the activity returns. So this is a case where we're not completely killing the cells off, but we're showing that deficits are induced, but you can also get recovery. And then in the addition of this compound, ZP1609, which is a gap junction promoter, we see the deficits are reduced and you get a faster recovery, showing proof of concept of the platform itself. Now, some of the limitations of the study were, one, they were unpatterned cardiomyocytes. Two, these are spontaneous electrical measurements, not stimulated. So moving on, what we wanted to do was increase the throughput of this platform. How did we want to do that? We wanted to add the cardiac mechanical function. We wanted to add real-time monitoring inside the incubator, not having to take it out. We wanted to measure vasoconstriction dilation, add functional readouts for the vasoconstriction, multi-organ system integration, make it high throughput, and then remote monitoring. So moving on to what the system now looks like as opposed to just an MEA. The multi-organ system we designed looks like here in the panel A. It consists of a top and bottom housing and two middle layers of gaskets. And then we did some fluid dynamic modeling to show the assembly stress and also looking at the velocity, shear stress, etc., to optimize both the flow rates and shear stress so we're not causing undue damage to the cells. And then here's finally what the end product looks like, where we use a snapfill for the vasoconstriction model itself to look at the barrier integrity and also the plater on cantilevers. And it also consists of the cardiac microelectrode array. So in terms of making the electrophysiology high throughput, here's a schematic of how we did it. Essentially, we took what could only be done once at a time, and then we added more amplifiers and multiplexed it a bunch, right? So what that helped us do was, and we also added stimulation capabilities. What that allowed us to do was go from doing one system at a time, essentially one electrode outside the incubator, to now be able to do up to 16 systems inside the incubator all at once. And it also added the ability to be able to stimulate. Now, when we're able to stimulate, you can see when you add a stimulation pulse on the first electrode here, you get a conduction path across going in a U pattern, and you can see the shift in the conduction path, and that's how the conduction velocity is measured. So So moving on to the validation of the system itself and making sure the stimulation is not doing anything to the cardiac cells. Here's a waveform that we usually end up getting from the system. Again, very similar to what you might see in the clinic, looking at a QRS T-wave sort of pattern. In the middle panel here is, you see the stimulation pulses, or the artifacts as we call them, followed by the actual signals. And what we end up doing is pace them at a certain frequency to be able to look at how well they perform. What you see on the right here is, on the top panel, it's showing the beat frequency over time after stimulation, which is showing it's consistent over a 48-hour period without any changes in RR variability, etc. What this essentially showed us was the stimulation pulses that we chose in terms of the current, pulse width, etc. were all valid, and it did not affect our system negatively. Moving on to the environmental control chamber itself that we designed, because now we wanted to add all of these electronics into the incubator without having to take them out. Here's a schematic of what that looks like, right? This overall setup still goes into the incubator, but it's in a self-contained box that then goes on a rocker, because the rocker is what drives the flow in our case. We set the parameters for the rocker based on the degree of tilt and the number of oscillations per minute to get our desired flow rate. Now, inside the box that I described, you're going to have sensors to measure the oxygen concentration and the carbon dioxide concentration, both in the air and also inside the medium. We're also looking at measuring temperature, humidity, and like I said, the medium oxygen concentration. What's also inside is all the high throughput measurement equipment. We have humidity control, and all of it's being recorded real time and transferred to the cloud. So here's an example of showing what that control looks like, where we can just program the protocol into the microcontrollers, and we can essentially make this do what we want it to. In this case, you're looking at showing a rapid ischemic event over a 20-hour period, and then showing reperfusion. What you're seeing in blue is the concentration in the air. That's why it drops so rapidly, versus what you're seeing in the red is the concentration inside the medium in the system. So that's what your cells are seeing. As you can see, that's more so over a 4-hour period as opposed to the rapid decline in the environmental concentration. And then what you also see in the continuous monitoring is that without any ischemic event, it's fairly consistent. You don't see much changes in the conduction velocity. Here's what that whole setup actually looked like in the prototype phase. We use a 5-box microcontroller right now, which is a commercial one, to measure the oxygen concentration inside the medium. So this is the same thing I showed in the previous graph, which is the oxygen concentration in the system. And when we look at what that does to the cells, you see the conduction velocity starts off at 100%. You see it decline over the period of ischemia, and then you see it come back over the reperfusion period. Very similar to what we saw previously. But what we were now able to do is show this in a high throughput fashion over 8 systems in this case, but it can also go up to 16. We already talked about the electrophysiology part, so now moving on to the mechanical part. How do we measure that? We talked about the cantilevers, and like I mentioned, they're just these paddles. Here we just show that we had to develop a bunch of electronics, and showing different deflections produce different qualities of signal. Because that leads us into the cooler parts of the technology, which is looking at piezoelectric cantilevers. Why did we want to do the piezoelectric cantilevers? It's because previously we talked about the laser-based system, for which we have to take the entire system out of the incubator, because that whole system's about that big. With the piezoelectric cantilevers, we never have to take them outside the incubator, because essentially any change in the mechanical, essentially a force is being converted into a change in charge, right? So here is just showing the fabrication process, end product, and on the bottom panel here, you can see the cells when they're grown on the cantilevers. They show no cytotoxicity, and they align well. And when actually measured, here were the kind of signals that we were getting, the mechanical force measurements. And just to show that we can get changes in response by adding 3 micromolar epinephrine, you see a change in the beat frequency in this case. So any changes in force now can be detected using these cantilevers in situ. So that's good for the cardiac cells, but what about for the smooth muscle cells? Because the piezoelectric effect is very rapid. It can only detect very sharp changes in the force, but when it comes to the smooth muscle contraction, it's going to be a lot slower. To detect that, we need the piezoresistive cantilevers, which more give a change in resistance to a change in force. Again, showing the fabrication process, the end product, the fabricated chips, the test setup that was used. So in this case, we haven't added the smooth muscle cells on these here to show the proof of concept. What we did do was build up an actuator jig with a micro needle at the end, and showing that different amounts of deflection produces the deflection that's readable from the electronics, which can then be used to look at changes in force. Now finally, we also wanted to look at the barrier integrity of the smooth muscle model. So here's a simple vasoconstriction model that the first iteration, right? It was just co-culture of human aortic smooth muscle cells and human aortic endothelial cells on a permeable membrane. And one of the things that they wanted to look at was what is the changes in the barrier integrity. And usually TER is a measurement that's used. It's transepithelial or endothelial electrical resistance, right? So all that's doing is based on Ohm's law, you're applying a current across the cell layer and measuring a voltage. And any change in the barrier integrity is going to cause an effective change in the circuit, which causes an effective change in the resistance. Again, we built a custom unit instead of using the commercial one here because we wanted to take it to high throughput. What we showed here in the panel B is the validation by comparing it with the commercial version versus the version we developed on the x-axis. We get very good agreement, and the overall error that we had in this case was within 15% of the commercial device. So again, this allowed us to take it to commercial. So now we were able to integrate all of this, and all of these readouts now can be got at once, was the main goal of ours in the conclusion. So essentially, my conclusion and next steps is we've developed an integrated platform in situ, which can be used to study cardiac ischemic events that has the functional readouts for tear, cardiac electrophysiology, cardiac force, and smooth muscle contraction. We can control and measure the oxygen and carbon dioxide concentration, both in the environment and inside the device. We can program any protocols that we want to control the ischemic event. And what that allows us to do is do all kinds of remote recordings, right, since everything is IoT-based. And then finally, we developed a multi-organ system into which we could house all these different devices and the different organ modules that would then fit into these boxes, and we be able to get the measurements. Now, in terms of next steps, the key step is to, one, take the vasoconstriction dilation model to the next level from the more basic model that we're using right now, and start doing high throughput screening on these with some test drugs that we're interested in to show changes and see how that compares to the clinic. We've also used this environmental control chamber in other studies, like to study malaria parasite in a multi-organ setting. So such a in situ product is not only useful for cardiac ischemia, but it could be used for a multitude of things. So you don't necessarily have to use the environmental modules. You can use only the force and electrophysiology modules. You can study muscle, etc. And then I'd like to acknowledge Dr. James Hickman, our CSO, and my engineering team at Hesperus, and also the scientists that assisted with this. I'd also like to thank the NIH for their support. Thank you.
Thank you, Sriram. Any questions from the audience?
Yes, there is one.
Hi, thanks for the talk. My name is Suji. I'm from Harvard University. I was curious about the, so when we culture the cells, it's important to consider the mechanical property of the cell culture environment. But
I can't really hear you, sorry. I can't really hear you.
Okay. When we culture the cells, I think it's important to think about the mechanical property of the cell culture environment. Mm-hmm. But it looks like when you culture the cells on the cantilever, it looks like the substrate itself looks stiffer. So have you considered about culture cells like in a softer microenvironment?
I don't necessarily still think I understood the question correctly. Did you ask if the surface itself is slippery on the cantilevers, so do we coat them with something?
Mechanical properties, like, or have you considered using hydrogel coating on top of it and then measure the mechanical property of the surface?
I think what she's asking is, because your cantilevers are a lot stiffer than your other substrates, have you looked at the mechanical properties of the cells itself, or have you thought about using any hydrogels to compensate for that? Was it that?
Um, no, we haven't thought about using alternate materials, at least add coatings onto the cantilevers themselves. Right now, we back calculate the force for the cantilevers based on Stoney's equation because we know the mechanical properties of the cantilevers. We do the testing to look at the Young's modulus, etc. But no, we haven't thought about adding hydrogels, etc. But you're right that adding that could increase the sensitivity further. So that's a good point.
Any more questions?
There is one.
Great talk, thank you. I was wondering whether you've performed any transcriptomics analysis on the cells and compared them to probably like a what's happening in a patient situation to see whether your ischemic insult is actually comparable to what a patient feels.
So I understand your question was, have we compared the changes in the cardiac data from the in vitro system to the in vivo scenario? Usually, so what we have shown in terms of comparison is that we've shown the changes in the inversion of the T waves, they match up, and we show that we get the range of the CV changes match up. But since we don't exactly know what percentage of ischemia was happening in vivo versus what we see in the system over that certain timeline, it's hard to exactly compare. But what we did show was what the changes in conduction velocity that you get over 70% in vivo is something we also get in vitro, and we get the inversion in the T waves. And we get complete shutdown over longer time periods that match up with the in vivo.
We have another question here.
Thanks. A very nice talk. I was wondering, how would you compare, in terms of your vasoconstriction part of the model, how would you compare your result to what you see physiologically? Because the situation is very different in the sense that the relationship between the endothelial cells and smooth muscle cells, is different in your system than it would be physiologically with the muscle wrapping around. And I can see where you'd get some measure from the tear about the constriction, but I don't see how you'd relate that to a physiological response.
It's more so by using the piezoresistive cantilevers to look at the change in the constriction and dilation itself.
Right. So in one case, in vivo, you're looking at, what's relevant is the dilation or constriction. And in the experiment, I guess what you're measuring is just as the smooth muscle gets activated, that it pulls on the endothelial cells and the tear changes?
That's actually an excellent question that we're also dealing with. On the smooth muscle component itself, what I would say is that, like I said, the rudimentary phases, what we can use it for is whilst creating new compounds, looking at, like you said, the activation and the inactivation, and looking at any toxicity. But you're right, that is something we have to think more. I don't think I have an answer for you.
Thank you very much.
All right, then let's just thank our speaker, and thank you so much, Sriram. We can head for lunch.